There are whispers in the fabric of reality, forces that shape everything yet leave no trace. You can't see them, you can't touch them. But without them, atoms would fall apart, light would vanish, and time itself might lose meaning. These aren't particles of matter, they're particles of force, bosons. They don't build the universe, they bind it. They are the reason light moves, the reason gravity pulls, the reason you aren't just a scattered cloud of atomic dust. Most people have never heard of them, even fewer understand them. But every second you exist, you owe to their invisible grip. What are bosons? And are they even real? Imagine a universe without light, without gravity, without the forces that hold atoms together or guide the stars through galaxies. That's a universe without bosons. They are the invisible threads that stitch together the very fabric of existence. And yet, unlike the more well-known particles like electrons or protons, bosons live in a strange and ghost-like world. A world where the rules of matter break down. A world where many can occupy the same state at the same time. A world that seems more like a whisper from the quantum void than something solid and real. To understand what makes bosons so strange, we need to rewind to the basics. In the zoo of quantum particles, there are two great families, fermions and bosons. Fermions are the building blocks of matter, electrons, protons, and neutrons. They obey the Pauli exclusion principle. No two fermions can occupy the same quantum state. That's why atoms have structure. That's why you can't walk through walls. Bosons, on the other hand, don't follow this rule. They are the force carriers. Photons carry electromagnetism. Gluons hold atomic nuclei together. W and Z bosons mediate the weak force, and the Higgs boson gives mass to other particles. If fermions are the bricks of the universe, bosons are the invisible mortar. They allow matter to interact. But the strangeness of bosons goes deeper. Because they can pile on top of each other in the same state, they create bizarre quantum phenomena. Bose-Einstein condensates, for example, are formed when bosons are cooled to near absolute zero and suddenly begin to behave like a single quantum entity, like a wave of matter. This trait alone makes bosons alien to our everyday intuition. They don't behave like particles in the classical sense. In fact, some physicists argue that calling them particles at all is misleading. Their statistical behavior, Bose-Einstein statistics, was formalized in the 1920s by Indian physicist Satyendra Nath Bose and extended by Albert Einstein. That collaboration alone gives bosons their name. But for decades, bosons remained an abstract idea, a mathematical necessity in our quantum models. It wasn't until experimental physics caught up that we began to truly observe and manipulate these ghostly beings. Photons were easy, they're everywhere. But gluons? Impossible to isolate. W and Z bosons, detected at massive particle colliders like CERN in the 1980s. And the Higgs boson, a decades-long quest that culminated in its discovery in 2012 at the Large Hadron Collider. Each discovery confirmed a part of the Standard Model, the prevailing theory of particle physics. And yet, despite their centrality to that model, bosons remain largely mysterious. They exist at the edge of detectability, and some, like the hypothetical graviton, haven't been seen at all. Their behaviors in extreme conditions, such as those near black holes or in the early universe, might hold the key to new physics. Here's where things get even more philosophical. Are bosons simply force-transmitting particles in the same way a thrown ball carries momentum? Or are they better understood as disturbances in quantum fields, ripples in invisible fabrics that permeate all of space? In that case, what we call a boson is just a localized excitation, a blip, a flicker. This isn't just semantics. It points to a deeper truth about the nature of reality. And perhaps if we look closely enough, the strange rules that govern bosons will reveal something astonishing. Not just about the particles themselves, but about the very structure of space, time, and the forces that knit them together. because understanding bosons isn't just a curiosity, it's a window into the quantum world, a place where intuition fails and reality turns strange. And if bosons are real, then reality itself might be far stranger than we ever imagined. To understand bosons is to confront one of the deepest philosophical and scientific truths about reality. Not everything that exists takes up space. Unlike the matter particles we know, electrons, protons, and neutrons, bosons are not particles of substance, but particles of interaction. They are the mediators of nature's fundamental forces, and to grasp them, we must first grasp what it means to transmit a force in the first place. Imagine a game of catch in deep space. You and a partner float motionless, tossing a ball back and forth. Each time you throw the ball, you push yourself slightly backward. When your partner catches it, they recoil too. There is no tether, no string between you, only the ball, passed invisibly through a void, creates the sense of connection. In the quantum world, that ball is a boson, and every force you've ever felt, from the warmth of sunlight on your skin to the gravitational pull that anchors you to Earth, comes down to bosons exchanged in a grand invisible game of catch. There are four fundamental forces in the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each is governed by its own boson. The photon is the boson of electromagnetism, responsible for light and all electric and magnetic effects. Gluons hold atomic nuclei together through the strong force. W and Z bosons mediate the weak force, responsible for radioactive decay. And the graviton, if it exists, is the hypothetical boson of gravity, yet to be detected. These are known as the gauge bosons, the elite messengers of the standard model of particle physics. Unlike fermions, which make up matter and obey the Pauli exclusion principle, meaning two identical fermions can't occupy the same quantum state, bosons follow Bose-Einstein statistics. This means they can pile into the same state with no problem. In fact, the more bosons in one state, the more likely others are to join them. This bizarre behavior leads to phenomena like lasers, where countless photons move in perfect harmony, and Bose-Einstein condensates, exotic states of matter where atoms behave like a single superatom. Take the photon, for instance. It is massless, has no electric charge, and always travels at the speed of light. Yet it is responsible for everything from photosynthesis to radio signals, from the colors in a rainbow to the electric spark that lights a fire. It is the most familiar boson, and yet one of the strangest. The moment you understand that light is both wave and particle, both a shimmering ripple through space and a quantized packet of energy, you are entering the domain of bosons. Then there are gluons. If photons are gentle messengers, gluons are brutal enforcers. They mediate the strong nuclear force, the mightiest force in nature, capable of overcoming the electric repulsion of protons packed tightly in a nucleus. But gluons do something unique. They carry the very charge they interact with. Photons carry no electric charge, but gluons carry color charge, a property of quarks. This makes the strong force incredibly complex. Gluons interact not just with quarks, but with each other, creating a tightly woven web inside every proton and neutron. The weak force, mediated by the W and Z bosons, is perhaps the most peculiar of all. These bosons are massive, unlike the photon and gluon. In fact, the W boson is nearly 80 times heavier than a proton. This makes the weak force incredibly short-ranged, so short it's barely felt outside the nucleus. Yet it plays a vital role in the fusion reactions that power the sun and in radioactive decay processes that shape the elements of our universe. Without the weak force, hydrogen would never become helium, stars would never burn, life would never begin. These are the known, observed bosons. But there is one more, a particle so elusive, it took nearly 50 years to confirm its existence. The Higgs boson. The Higgs is not like the others. It does not mediate a force in the traditional sense. Instead, it arises from the Higgs field, a quantum field that permeates all of space. As particles move through this field, they interact with it. The stronger the interaction, the more mass they acquire. It's as if the universe is filled with a kind of cosmic molasses. Some particles glide through easily and remain light. Others get bogged down and become heavy. The Higgs boson is the ripple, the excitation of that field. When the Higgs boson was finally detected in 2012 by the Large Hadron Collider, it confirmed the final missing piece of the Standard Model. But it also opened new doors. Why does the Higgs field exist at all? Why does it have the value it does? And why do bosons behave so differently from matter particles? Bosons aren't just curious artifacts of theory. They are the reason atoms hold together, the reason forces can reach across space, the reason there is structure instead of chaos. But even now, as we observe their effects and detect their signatures, we are haunted by deeper mysteries. Do bosons truly exist as particles? Or are they merely the mathematical shadows of deeper, invisible rules? In a universe defined by silence and symmetry, bosons are the ghostly intermediaries of reality's unseen transactions. They carry the push and pull, the flickers and fusions, the light and the gravity. But are they real? Or are we watching shadows on the cave wall, never quite able to grasp what moves behind them? As we move forward, we'll delve into how bosons differ from matter particles at a fundamental level, not just in behavior, but in the very rules they obey. What we uncover next may forever change how we define what it means to exist. There's a quiet order to the chaos of the cosmos, rules that govern how everything holds together or falls apart. And behind these rules stand the bosons, not as overseers, but as messengers. Couriers of invisible orders passed between the particles of matter. They do not build the universe, they bind it. In the grand architecture of physics, four fundamental forces shape everything: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces, though radically different in strength and scale, operates through a specific kind of boson, a force carrier. These bosons don't push or pull in the traditional sense. Instead, they mediate interaction. They are the exchange particles, the handshakes and shoves between fermions. The universe runs on these exchanges at every level. Let's begin with the most familiar, the photon, the force carrier of electromagnetism. Photons are massless, chargeless, and they always move at light speed. They are bosons of light itself, but also of every electric and magnetic interaction. When a magnet pulls a paperclip or your hand feels the warmth of sunlight, it's not some abstract field reaching out. It's photons being exchanged, subtle, countless interactions at the speed of causality. Electromagnetism is extraordinarily powerful compared to gravity, yet it's governed by simple rules. Photons don't carry electric charge, so they don't interact with each other. This simplicity makes the electromagnetic force long-ranged and easy to work with. It also makes the photon one of the cleanest bosons to study. In fact, photons are so well behaved that they are the foundation of quantum electrodynamics, one of the most precisely tested theories in all of science. Now, step into the nucleus, where things become less elegant and far more intense. The strong nuclear force is a monster. It is 100 times more powerful than electromagnetism, but operates at a scale smaller than the size of a proton. This force holds quarks together to form protons and neutrons, and then holds those protons and neutrons together inside atomic nuclei. Without it, every atom would explode into subatomic dust. The carriers of this force are the gluons, 8 kinds, each massless but uniquely complex. Gluons, unlike photons, carry the very charge they act upon, color charge, a quantum property of quarks. This means gluons interact not only with quarks, but with each other, forming an intricate, self-interacting field. It's a violent, tangled mess, what physicists call quantum chromodynamics, or QCD. You will never see a free quark or a free gluon. The strong force is so strong, it confines its players. Try to pull quarks apart, and the energy you put in simply births more quark-antiquark pairs. It's like stretching a rubber band that refuses to snap. Instead, it creates new rubber bands. This is why you and everything around you appears stable. The chaos beneath is caged by gluons. Next comes the weak nuclear force, a force so strange and subtle, it almost seems like a glitch in the code of reality. Its bosons, the W and Z bosons, are massive, almost absurdly so. The W boson weighs in at nearly 80 times the mass of a proton. The Z boson is even heavier. This incredible mass gives the weak force an extremely short range, less than the width of a proton. But don't let that fool you. The weak force plays a central role in some of the most important processes in the universe. The sun shines because of the weak force. Radioactive decay happens because of it. Neutrinos, the ghost particles of the cosmos, interact almost exclusively through it. And it is through the weak force that particles can change identity. A neutron becomes a proton, a muon becomes an electron. These transformations are part of why the periodic table exists at all, and without them, the elements that make up life would never have formed. But now, we must look outward and downward. The final force, gravity, is the most familiar and yet the most mysterious. It shapes planets, stars, galaxies. It sculpts the very fabric of space-time. And yet it is unbelievably weak on the quantum scale, so weak that a single magnet can lift a paperclip against the gravitational pull of the entire Earth. Why is gravity so weak? No one knows. It doesn't fit comfortably in the quantum world. There is no confirmed boson for gravity. But physicists suspect one exists, the graviton. A hypothetical massless particle with a spin of 2, the graviton would be the quantum mediator of gravity, completing the roster of the fundamental forces. But so far it remains a ghost, undetected, possibly undetectable. We may need a theory of quantum gravity to find it, or to realize it doesn't exist at all. These 4 forces and their bosons form the foundation of the standard model of particle physics. Together, they describe almost everything we observe, from the structure of atoms to the behavior of light to the nuclear reactions in stars. The standard model is a towering achievement, but it's also incomplete. It does not account for gravity. It does not explain dark matter, and it cannot explain why the forces are so different in strength. Yet within this model, the bosons play a central role. They are not side characters. They are the carriers of change, the messengers of motion, the reason why any 2 particles can influence each other at all. Without bosons, fermions would exist in isolation. Matter would have no force to bind it, no energy to move it, no rules to guide it. Bosons are the language of interaction. They are what makes physics do something rather than merely be something. Every time a charge feels a field, a nucleus fuses, a compass swings, or a light turns on, a boson is speaking. They are nature's communication protocol, and they never say a word. In the world of quantum particles, nothing is ever quite what it seems. Just when you think you've grasped the simplicity of bosons, those force-carrying entities that glue the universe together, quantum mechanics flips the table and introduces something stranger: composite bosons. These are not elementary particles like photons or gluons. Instead, composite bosons are made from combinations of matter particles, fermions, that somehow defy expectation and behave as bosons anyway. It's a bit like building a bridge out of bricks, only to find that the bridge itself bends like a rope. The whole becomes something different than the sum of its parts. To understand this paradox, let's revisit one of the most fundamental rules of quantum physics. Fermions, which include electrons, protons, and neutrons, obey the Pauli exclusion principle. No 2 identical fermions can occupy the same quantum state at the same time. This rule is the reason matter has structure. It's why electrons arrange themselves in shells around atoms. It's why white dwarfs resist collapsing under gravity. It's why you don't fall through the floor. Bosons, on the other hand, play by different rules. They can occupy the same state. Not only that, they prefer it. The more bosons in a state, the more likely others are to join. It's this statistical freedom that allows photons in a laser to move in perfect lockstep. That's the foundation of Bose-Einstein statistics. Now here's where it gets weird. If you take two fermions, each stubbornly obeying the exclusion principle, and bind them together under certain conditions, the resulting pair can act like a boson. It no longer follows the rules of its ingredients, it follows the rules of its symmetry. In quantum mechanics, particles are described by wave functions. When two fermions pair up, their combined wave function becomes symmetric. That's the signature of a boson. And that symmetry isn't just a mathematical curiosity. It governs how the particle behaves in the real world. Take helium-4, for example. Each helium-4 nucleus contains 2 protons and 2 neutrons. All of these are fermions, but add up their spins, and the total is an integer, a defining characteristic of bosons. So despite being made entirely of fermions, helium-4 atoms behave like bosons, and that allows them to do something incredible. When you cool helium-4 to just a few degrees above absolute zero, it undergoes a quantum transformation into a superfluid. In this state, it flows without viscosity, without friction, climbing up walls, leaking through cracks that seem sealed, spinning forever in a container without ever slowing down. This is not a party trick. It's a macroscopic quantum effect, and it only happens because helium-4 atoms act like bosons. Another striking example is found in the Cooper pairs that form inside superconductors. In certain materials, at low temperatures, electrons, which are fermions, begin to form pairs. Each pair acts as a composite boson. These pairs can flow through the lattice of a metal without resistance, because they are not scattering like individual electrons. They're moving in a shared, synchronized quantum state. This is what allows superconductors to conduct electricity perfectly without losing energy as heat. Composite bosons reveal something profound about quantum mechanics. Identity is not fixed. Behavior depends not just on what something is made of, but on how it moves, how it spins, and how it interacts with others. The whole is truly greater than the sum of its parts, because the rules themselves change when particles combine. And this principle isn't limited to low-temperature lab tricks. In fact, it may be woven into the very structure of the cosmos. In the early universe, moments after the Big Bang, particles weren't organized into neat atoms and molecules. They swirled in a dense, high-energy plasma. In such a state, bound states like mesons, made of a quark and an antiquark, acted as bosons. These short-lived composite bosons may have influenced how matter cooled, how energy was distributed, and how the forces of nature separated into the distinct interactions we see today. Mesons themselves are fascinating. Though they are not force carriers like photons or gluons, they do mediate the residual strong force that holds atomic nuclei together. That makes them participants in one of the universe's most important balancing acts, keeping protons and neutrons close enough to stick, but far enough not to collapse into each other. And then there's the curious case of magnons, phonons, and excitons, quasi-particles that behave like bosons in solid-state systems. These are not particles in the traditional sense. They are emergent phenomena, ripples in a material's structure that act like particles, complete with mass, spin, and momentum, and many of them too are bosonic. What does this tell us? It tells us that bosons aren't limited to a fixed roster of elementary particles. They can emerge. They can arise from interactions. They can be formed, shaped, and dissolved by the quantum dance of fermions beneath. This adaptability suggests that bosons are not just objects, but patterns. They are collective behaviors, modes of communication, coherent whispers in the field of existence. And it raises an unsettling question. If bosons can emerge from underlying complexity, could the elementary bosons we know, like photons or W and Z bosons, also be emergent from some deeper layer of physics? Are we seeing the tip of a quantum iceberg? Are bosons the surface signals of an ocean we can't yet detect? As we move forward, we'll explore a phenomenon that brings bosons to the brink of magic: Bose-Einstein condensation. It is the coldest, strangest state of matter we know, a state where bosons lose their individuality and fuse into one shared quantum identity, a single enormous wave function, a glimpse perhaps of what pure unity looks like in the physical world. But before that, take a moment to let this sink in. The universe permits its laws to bend under the weight of combination. It allows opposites to merge and become something new. And in that process, it reveals a secret about reality. That identity in the quantum world is not about what something is, but what it becomes when it belongs to something greater. Imagine cooling a substance so close to absolute zero that motion itself nearly stops. Molecules slow, atoms settle. The wild vibrations of heat fade into eerie stillness. But just before everything freezes solid, something miraculous happens. The particles, bosons in this case, don't disappear or break apart. They do something far stranger. They merge, not physically like drops of water blending together, but quantum mechanically. Their individual wave functions begin to overlap until the distinction between one particle and another vanishes. They all begin to act as one, a single coherent entity. This is the Bose-Einstein condensate, a state of matter so rare and alien, it didn't exist in any lab on Earth until the late 20th century. And yet, it was predicted over 70 years earlier by two giants of physics, Satyendra Nath Bose and Albert Einstein. In the 1920s, Bose had been working on the statistical mechanics of photons. He realized that light particles didn't follow the same statistical rules as particles of matter. He sent his work to Einstein, who immediately saw its brilliance and extended the math to atoms themselves. Einstein proposed that under extreme cold, bosonic atoms would condense into a single quantum state. It was a theoretical marvel, but for decades it remained just that, a theory. Fast forward to 1995. Physicists Eric Cornell and Carl Wieman managed to cool a gas of rubidium atoms to less than 170 nanokelvin, less than a billionth of a degree above absolute zero. And when they looked closely, they saw it, a Bose-Einstein condensate. It was real. The atoms had surrendered their individuality. The quantum world had spilled into the macroscopic. To appreciate how strange this is, consider what usually happens when you add more particles to a system. In most cases, the complexity increases. Atoms bounce off each other. Waves interfere. Chaos grows. But in a Bose-Einstein condensate, adding more bosons brings more order. They pile into the same state. The quantum behavior doesn't get lost, it gets amplified. It's like watching a crowded concert where everyone starts dancing in perfect unison, without a single word spoken. Not out of chaos, but out of shared identity. In this state, matter exhibits bizarre properties. It flows without viscosity, like a superfluid. It can creep up the walls of its container. It behaves, in essence, as a single giant atom. And the wave function that describes it is no longer a probabilistic haze. It's sharp, coherent, unified. This has enormous implications. First, it confirms one of the most radical predictions of quantum mechanics, that particles are not isolated dots in space, but wave-like entities whose identities can fuse under the right conditions. That behavior isn't theoretical. It's observable, repeatable, and to some extent controllable. Second, Bose-Einstein condensates give us a new lens for exploring quantum phenomena at a visible scale. Usually, quantum effects are buried deep in the world of the ultra-small, electrons, quarks, or photons. But in a condensate, the behavior is big enough to measure, manipulate, and observe directly. It's like turning up the volume on the quietest whisper in the universe. Third, it opens doors to technology that might seem like science fiction. Because Bose-Einstein condensates are highly sensitive to external forces, they can be used in ultra-precise sensors. Imagine gyroscopes and accelerometers orders of magnitude more accurate than anything we have now. That's already happening in experimental quantum navigation systems and gravitational sensors. Even more provocative is the idea of using condensates in quantum computing. Because the particles in a condensate are entangled in the same quantum state, they could, in theory, be used to encode and manipulate information in profoundly efficient ways. It's early, and the technical hurdles are massive, but the door is cracked open. And then there's the cosmic angle. Some physicists speculate that dark matter, the mysterious, invisible mass that outweighs all visible matter in the universe, might exist in a form akin to a Bose-Einstein condensate. Perhaps entire galaxies are embedded in a giant universe-spanning wave function of unknown bosons. If true, it would mean that the strangest state of matter in the lab could also be the most common state of matter in the cosmos. But for all its potential, the Bose-Einstein condensate also confronts us with a humbling truth. The universe is not what it seems. At room temperature, matter feels stable, tangible, and distinct, but lower the energy, strip away the noise, and a different picture emerges, one where identity blurs, individuality fades, and unity reigns. Bosons, freed from the rules that constrain matter particles, show us that the quantum world is not just weird, it is deeply connected. When Einstein extended Bose's idea, he likely didn't imagine we'd one day hold these condensates in our hands, or use them to test the edges of physics. But here we are, and every time we cool a gas of atoms to near zero and watch them become one, we catch a glimpse of something profound, the unity beneath complexity, the simplicity beneath chaos. As we continue, we'll move deeper into the theory that underlies all of this. Quantum field theory, the language in which bosons truly speak. There, we'll see that bosons aren't really particles at all, but ripples in invisible fields that permeate all of space, fields that might just be the truest fabric of reality. To truly understand bosons and why they behave so differently from matter, we have to let go of one of the oldest ideas in science, that particles are tiny, solid things bouncing around in space like marbles. That's not how reality works, not at the smallest scales. In the modern view, everything in the universe is made of fields, invisible, continuous quantum fields that extend through all of space and time. Electrons, photons, quarks, and even the Higgs boson. They're not tiny dots floating in a vacuum. They're ripples in these fields, local excitations, vibrations of something deeper and more fundamental. This is the foundation of quantum field theory, or QFT, the most accurate and powerful scientific framework ever created. In quantum field theory, the entire universe is described as a vast ocean of overlapping quantum fields. Each type of particle has its own field. There's an electron field, a quark field, a photon field, a gluon field, and yes, a Higgs field. What we call a particle is really just a blip in one of these fields, a wave packet, a momentary oscillation, like a ripple flickering across the surface of a pond. This is where bosons begin to make sense. Because bosons aren't things, they're patterns. Take the photon. It's not a little bullet of light zipping through space. It's an excitation of the electromagnetic field. When that field vibrates just right, a photon is born. That's what a laser beam is, a flood of electromagnetic field disturbances, perfectly aligned. The gluon. It's a ripple in the strong force field, exchanging color charge between quarks. The W and Z bosons. They're disturbances in the weak field mediating radioactive decay. And the Higgs boson? It's a tremor in the Higgs field, a field that, unlike others, has a non-zero value even in empty space. A field that gives mass to particles as they move through it. In this view, bosons are the voice of the universe's invisible structure. They are how one part of a field communicates with another. They're not things thrown from place to place. They're messages, exchanges, flickers of interaction.
Even forces themselves are reimagined.
You don't feel the electromagnetic force because a particle pulls on you directly. You feel it because your electric charge disturbs the electromagnetic field, and that disturbance is felt by another particle nearby. The field does the work. The boson, the photon, is just the ripple that carries the information. And this is what makes bosons so strange and so powerful. They aren't subject to the same restrictions as fermions. They don't mind sharing space. In fact, they encourage it. Because in a field, ripples can amplify each other. They can sync up. That's why lasers are possible. That's why Bose-Einstein condensates emerge. That's why bosons are the carriers of coherence, while fermions are the carriers of exclusion. Think of it like this. Fermions are the bricks of reality, while bosons are the forces that bind the bricks together and the music that keeps them dancing. Quantum field theory is not just a theory of particles. It's a theory of interactions, a theory of how the universe communicates with itself. And bosons are at the heart of that communication. But here's the twist. Even though QFT is breathtakingly accurate, it predicts the magnetic moment of the electron to 12 decimal places, it's not complete. It breaks down under extreme conditions. It doesn't include gravity, and it leads to infinities that physicists have to re-normalize away, like sweeping dust under a rug. And that's where bosons once again point to a deeper truth. Because gravity, the one force still missing from a quantum field description, is also thought to have a boson, the graviton. We haven't seen it, but if it exists, it would complete the set. It would mean every fundamental force in nature is carried by a boson. Every interaction is a ripple. Every change in the universe is a vibration in an invisible field. This idea that reality is not made of particles but of fields may sound abstract, but it's the closest science has ever come to describing what the universe actually is. And bosons are our way in. They let us probe the invisible, touch the untouchable. They're not just force carriers, they are evidence that something deeper is at work, that there is a code, a pattern, a structure beneath the randomness. The next time you feel warmth on your face from the sun, you're not feeling heat. You're being struck by a billion photons, ripples in a field that has no edges. The next time you flip on a light switch, what you're actually doing is exciting a quantum field, creating a wave that travels through space, bounces off walls, enters your eye, and is decoded by your brain. All made possible by bosons. But as elegant as this picture is, it raises a haunting question. If reality is made of fields, what makes the fields? In the quiet cold of deep space, far from stars and noise, a question stirs. Why does anything weigh anything at all? It's a question that haunted physicists for decades. In the standard model of particle physics, a masterwork of human understanding, particles like electrons, quarks, and W and Z bosons are predicted with exquisite precision. The theory works astonishingly well. But for most of the 20th century, it had one glaring flaw. It couldn't explain mass. Some particles had it, others didn't, and there was no reason why. It was as if someone had written the most beautiful symphony imaginable, but left out a key chord without which the entire composition fell apart. That missing chord was the Higgs boson. But to understand the Higgs boson, we need to talk about the Higgs field, the invisible ocean that fills all of space. Unlike other quantum fields which flicker and hum only when disturbed, the Higgs field has a constant, non-zero value, even in a perfect vacuum. It's always there, always on, like an invisible fog that clings to everything in the universe. Now imagine a particle moving through this fog. If it interacts strongly with the Higgs field, it slows down, like a swimmer trying to wade through molasses. That interaction gives the particle mass. If it interacts only weakly, it slips through easily, and its mass remains small. Photons. They don't interact at all with the Higgs field. That's why they have zero mass and travel at light speed. W and Z bosons. They interact very strongly, which is why they are incredibly massive, about 80 and 90 times heavier than a proton, respectively. And it's this mass that gives the weak force its short range, preventing radioactive decay from running wild across the universe. The Higgs mechanism, as this process is known, was proposed in the 1960s by several physicists, including François Englert and Peter Higgs. But it remained just a hypothesis, an elegant explanation with no experimental proof. To confirm it, scientists needed to do something extraordinary. They needed to see the Higgs boson, the quantized ripple in the Higgs field. But there was a catch. The Higgs boson is massive, roughly 125 times heavier than a proton, and extremely unstable. It decays almost instantly into other particles. To catch it, you'd need to smash particles together at unprecedented energies and sift through the debris for patterns that lasted just fractions of a nanosecond. Enter the Large Hadron Collider. Buried beneath the Franco-Swiss border, the LHC is a 27-kilometer ring of superconducting magnets that accelerates protons to near light speed and crashes them into each other. It's the largest, most complex machine ever built by humans, and it was designed in part to find the Higgs. On July 4, 2012, after decades of searching, two separate experiments at the LHC, ATLAS and CMS, announced the discovery of a new particle consistent with the predicted Higgs boson. It was a moment of triumph. One of the final pieces of the standard model had been found. Peter Higgs himself, then in his 80s, wept quietly in the audience. But for physicists, the celebration was bittersweet. Because the Higgs wasn't just a victory, it was also a mystery. For one, why does the Higgs field have the value it does? Why doesn't it vanish? Why doesn't it run wild and give everything infinite mass? This is known as the hierarchy problem. The Higgs mass is precariously balanced. Quantum mechanics predicts that it should receive enormous corrections from virtual particles, but it doesn't. It stays light, almost miraculously so. Why? Some theories propose that the Higgs is protected by supersymmetry, a hidden symmetry that pairs every known particle with a heavier partner. But the LHC hasn't found any supersymmetric particles yet. Others suggest the Higgs isn't fundamental at all, that it's a composite of smaller, unknown particles, or that it's part of a multiverse landscape where different universes have different Higgs values, and we just happen to live in one that permits stars, chemistry, and life. Whatever the answer, the Higgs boson is not just another boson. It's the first boson of its kind, a scalar boson, meaning it has no spin. All other known bosons have integer spin values, like one for the photon or gluon. The Higgs has spin 0. It is the only scalar particle we've ever seen.
That makes it unique.
And it might be just the beginning. There could be more Higgs bosons. In some versions of string theory or supersymmetry, there are 5 or more. They could interact with dark matter, help drive cosmic inflation, or even destabilize the vacuum of space. In fact, the discovery of the Higgs raised a terrifying possibility. Our universe might be in a metastable vacuum. That is, the Higgs field could be resting in a shallow energy valley, not the deepest possible one. A quantum fluctuation, perhaps triggered by a high-energy event, could cause the field to tunnel to a lower energy state. If that happened, the laws of physics themselves could change instantly, destroying everything in a wave of annihilation moving at the speed of light. This isn't science fiction. It's a real, if remote, implication of the numbers we've measured. But even without such doomsday scenarios, the Higgs remains a portal. It's the only known particle that interacts with the entire standard model, and yet seems to whisper about what lies beyond it. It connects matter and forces, mass and interaction, the seen and the unseen. It may hold clues to the greatest cosmic puzzles of all. What is dark matter? What happened in the first trillionths of a second after the Big Bang? Why does the universe exist at all? The Higgs is not the end of the story. It's the beginning of a deeper one. Gravity is everywhere. It binds planets to stars, sculpts galaxies from dust, and curves the very fabric of space and time. We feel its pull with every step. Yet of all the forces in nature, It is the one we understand the least. And unlike the other fundamental forces, we've never found its quantum messenger. We call it the graviton, a theoretical boson, never seen, never caught, but believed to exist if gravity is truly a quantum force like the others. And that's the problem. In the standard model, each force has a corresponding boson. Electromagnetism has the photon, the strong force has gluons, the weak force has W and Z bosons, and gravity has Einstein. His general theory of relativity describes gravity not as a force in the traditional sense, but as geometry. Massive objects curve space-time, and other objects simply follow that curvature. There are no quantum exchanges, no bosons flying back and forth, just the shape of space itself telling matter how to move. It works spectacularly well. General relativity has passed every observational test we've ever thrown at it. But it doesn't play well with quantum mechanics. At the smallest scales, the universe is jittery and chaotic. Particles flicker in and out of existence. Probability rules everything. But try to apply that same quantum logic to gravity, and the equations fall apart. Infinity creeps in. Predictions lose meaning. Something fundamental is missing. That's where the graviton comes in. If gravity can be quantized, then like all other forces, it must have a boson. The graviton would be massless, like the photon, and would carry a spin of 2, distinct from any known particle. It would transmit gravity through tiny, discrete exchanges, making space-time granular at the smallest scales. But no one has ever detected one. And that may not be a coincidence. Gravitons would interact incredibly weakly. Detecting one would require an experiment sensitive enough to register the gravitational pull of a single subatomic particle, a feat so far beyond current technology, it borders on the impossible. Yet the idea refuses to die. In fact, it's central to many attempts to unify physics. In string theory, gravitons are fundamental. Vibrating strings, infinitesimal loops of energy, create particles, and the graviton emerges as a vibration mode. Its presence is not optional, it's required. If string theory is correct, then gravitons must exist. Other frameworks like loop quantum gravity also attempt to describe a quantum theory of gravity, but they often dispense with particles entirely, describing space-time itself as woven from discrete loops or spin networks. Still, the allure of the graviton remains. It's not just about finishing the set of force-carrying bosons. It's about reconciling the two great pillars of modern physics, general relativity and quantum mechanics. Right now, they coexist like rival kingdoms, each ruling its own domain. Relativity governs the large, the orbits of planets, the dance of galaxies, the birth of black holes. Quantum mechanics rules the small, atoms, electrons, quarks, and the buzzing vacuum of space. They both work, they both predict, but they cannot be merged. Not yet. Gravitons are a kind of peace offering, an attempt to bring gravity into the quantum fold. If we could detect a graviton, it would open the door to a new understanding of space-time. Perhaps gravity isn't a smooth fabric after all. Perhaps it's built from something granular, something digital, at the Planck scale, so small that a single inch would still contain 6.2 trillion of them. This is not idle speculation. The very structure of reality may hinge on whether gravity is quantum or classical. If it's quantum, then space itself might be an emergent phenomenon, something that arises from deeper, more abstract principles. And then there are gravitational waves. In 2015, LIGO detected the first ripples in space-time caused by the collision of two black holes. It was a historic achievement. Einstein's predictions, written a century earlier, suddenly validated with chilling precision. Some hoped these waves might reveal signs of graviton behavior, tiny differences in how they travel, deviations from general relativity at high energy. But so far, the waves behave exactly as Einstein predicted, smooth, classical, continuous. Still, the possibility lingers. If gravitons exist, they would be the ultimate messengers, linking not just particles but entire frameworks of thought. Their discovery would mark a seismic shift in physics, revealing that space, time, and geometry are not the bedrock of reality, but structures resting on something even deeper.
But even if we never detect a graviton, the quest itself shapes how we think about the universe.
It reminds us that not all frontiers are defined by what we see. Some are defined by the questions we cannot yet answer, and the silence that follows. In that silence, physicists keep building new theories, new detectors, new dreams of unification. And somewhere, perhaps in the quantum haze that hovers near a black hole, the graviton waits, not as a particle, but as a whisper of what lies beyond the known. Long before there were galaxies, stars, or even atoms, the universe was a roiling storm of pure energy, hotter than 1 trillion suns, denser than anything we can now imagine. Time itself had barely begun to tick, and in that incandescent chaos, bosons reigned supreme. At the very birth of the cosmos, the first fraction of a second after the Big Bang, the universe was so energetic that matter as we know it couldn't yet exist. Temperatures were too high for particles like protons or electrons to form stable structures. Instead, the universe was a quantum soup, a blur of force fields and fluctuations. This was the bosons' domain. In those early moments, the fundamental forces were indistinguishable. Gravity, electromagnetism, and the nuclear forces were unified, woven together in a single superforce. But as the universe expanded and cooled, this symmetry began to break. Like ice forming on the surface of a pond, distinctions emerged where once there were none. The first force to separate was gravity. As it broke away from the others, space itself began to expand at an unimaginable rate, a phenomenon known as cosmic inflation. And while we don't know the exact boson that may have driven this inflation, physicists have theorized the existence of a particle, the inflaton, a boson tied to a field that caused the universe to stretch exponentially. If true, it would be the first domino to fall in the cascade of cosmic evolution. Next came the separation of the strong nuclear force. Gluons, bosons that carry this force, began to behave independently, binding quarks into protons and neutrons once temperatures cooled enough for hadrons to form. But back then, in what we call the quark-gluon plasma, quarks and gluons roamed freely, unbound and blazing. Only when the universe cooled to about 1/millionth of a second old did the strong force freeze out, locking quarks into particles that would eventually form the nuclei of atoms. Then, the electroweak force split. Before this moment, the photon and the W and Z bosons were essentially the same, part of a unified force. But at around 10 to the power of -12 seconds, the Higgs field activated. As the universe cooled past a certain threshold, the Higgs field spontaneously broke its symmetry. Bosons that interacted with this field, the W and Z, suddenly acquired mass. The photon, which did not interact, remained massless and became the boson of light. It was this Higgs phase transition that literally defined what would have mass in the universe. Without it, the W and Z bosons would be massless. Electrons wouldn't have mass, atoms wouldn't form. The cosmos would remain a mist of unstructured radiation. That's the quiet power of bosons. Not just as carriers of force, but as architects of phase changes, shaping how the universe evolves. And yet, even after all this structure began to form, the universe remained a war zone of annihilation. For every particle, there was an antiparticle, and when they met, they destroyed each other, releasing more bosons, more photons, more chaos. But something strange happened. For reasons still not fully understood, there was just a little more matter than antimatter. One extra particle per billion. That tiny imbalance meant that when the annihilation storm ended, a residue of matter remained, enough to build every planet, every star, every galaxy, and every person who has ever lived. And it was bosons, again, that played a role in that imbalance. The weak force, mediated by the massive W and Z bosons, violates a rule known as CP symmetry. a principle that says the laws of physics should behave the same if you flip matter into antimatter and reverse direction in time. But the weak force doesn't follow this rule perfectly, and that slight asymmetry may be the very reason anything exists at all. Fast forward to about 400,000 years after the Big Bang. The universe had cooled enough for electrons to combine with nuclei, forming neutral hydrogen atoms. Photons, trapped until now in a fog of charged particles, suddenly found themselves free to travel. That light is still traveling. We see it today as the cosmic microwave background, a soft glow of ancient photons that whispers the story of the universe's earliest days. These photons, bosons, are messengers from a time before structure, before stars, before memory. Even in those earliest patterns of temperature and density, we see the fingerprints of bosons. Tiny ripples seeded during inflation grew into the galaxies and cosmic webs we observe today. Without bosonic fields to transmit these ripples, there would be no large-scale structure at all. And so bosons didn't just exist in the early universe. They sculpted it. They triggered phase transitions that set the laws of physics. They mediated forces that determined what particles could exist. They carried away the heat, the chaos, the information. They defined how matter interacted, how symmetry broke, and how time began to move forward. The early universe was their workshop. The laws we take for granted today were written in that fiery script. And though the temperature has dropped and the chaos has cooled, bosons are still writing. Every beam of light, every atom bound together, every nuclear reaction in every star, all of it still sings the bosonic song. You don't need to look backward to find the fingerprints of bosons. You just need to open your eyes. There's a strange place at the edge of physics. It isn't found in distant galaxies or beneath towering particle accelerators, but in laboratories here on Earth. A realm not of heat, but of cold. So cold it's barely a whisper above absolute zero. And in this frozen silence, bosons reveal a secret unlike anything else in nature. It's called the Bose-Einstein condensate, a fifth state of matter, and one of the purest manifestations of quantum mechanics ever discovered. A phenomenon so bizarre that when Albert Einstein first predicted it in 1924, based on ideas from Indian physicist Satyendra Nath Bose, it sounded more like science fiction than science. The idea was simple but radical. If you take a group of bosons and cool them to near absolute zero, they won't just slow down like normal particles. Instead, they'll begin to merge, not physically, but quantum mechanically. Their individual identities blur. They overlap into the same quantum state, not just similar, but identical, millions, even billions of particles behaving as one single quantum entity. This is something fermions can't do. Because of the Pauli exclusion principle, no two fermions can occupy the same state. But bosons, free from that rule, are invited to gather. And the colder they get, the more irresistible that invitation becomes. Imagine pouring particles into a bucket, and instead of bouncing around randomly, they all suddenly fall into perfect synchrony, like a choir locking into the same note with infinite precision. That's what a Bose-Einstein condensate is. It's not just a new form of matter, it's a glimpse into the collective soul of quantum particles. But what does that look like? In 1995, nearly 70 years after it was first proposed, scientists finally made one. Using lasers and magnetic traps, physicists at the University of Colorado cooled a tiny cloud of rubidium atoms to just a few billionths of a degree above absolute zero. And then, it happened. The atoms blurred together. Instead of looking like a swarm of independent particles, they formed a single ghostly wave, spread out, coherent and eerily still. It wasn't a gas. It wasn't a liquid. It was a macro-quantum object, a quantum phenomenon you could see with the naked eye. This was the birth of a new frontier, ultra-cold physics. And at the heart of it all were bosons, showing that under the right conditions, individuality is optional. But Bose-Einstein condensates weren't just a scientific curiosity. They led directly to the study of superfluidity, another phenomenon where bosons behave in ways that seem to defy the laws of nature. A superfluid is a liquid that flows without friction, not just very smoothly, perfectly. Pour it into a container and it will climb the walls. Spin it and it will rotate in quantum vortices, tiny whirlpools with fixed, discrete energies. Superfluidity was first discovered in liquid helium at cryogenic temperatures. Below about 2.17 Kelvin, helium-4 atoms, bosons, enter a state where viscosity drops to zero. If you poke it, it doesn't resist. If you try to stop it, it slips through. Why? Because it's not behaving like individual atoms anymore. It's a quantum collective. Every particle part of the same undivided wave function. It knows where it's been, it knows where it's going, and no part can act without the others. This behavior extends to superconductors as well, materials that conduct electricity with zero resistance when cooled below a critical temperature. In these systems, electrons, which are fermions, form pairs, creating composite bosons. These so-called Cooper pairs move in perfect harmony, allowing current to flow endlessly without energy loss. Again, it's the bosonic principle at work, particles moving together in a shared quantum state, undisturbed by the usual chaos of heat and collisions. These discoveries aren't just scientific wonders, they have real-world consequences. Superconductors are already used in MRI machines, particle accelerators, and magnetic levitation trains. The potential for lossless power grids or quantum computers built on superconducting qubits lies just over the horizon. And Bose-Einstein condensates are now used to test theories of gravity, simulate early universe conditions, and explore quantum behavior at macroscopic scales. They're even being studied aboard the International Space Station, where microgravity allows for longer-lasting, more stable condensates. In a universe of chaos, bosons are the gatekeepers of order. They offer a path from individuality to unity, from randomness to resonance, and there's something poetic in that. We tend to think of physics as cold and clinical, equations and constants, mass and charge. But in the realm of bosons, we find something more, coherence, a tendency not toward isolation, but toward harmony. When bosons condense, they don't become less, they become more connected, more unified, more mysterious. And it makes you wonder, if the universe allows for this kind of quantum symphony at the smallest scales, what other forms of unity are still waiting to be discovered? If fundamental bosons like photons and gluons are the elegant architects of nature's forces, then composite bosons and quasi-particles are their uncanny cousins, ghostly echoes that emerge from collective behavior. They aren't elementary, they aren't fundamental, but in the strange theater of quantum mechanics, they act like bosons, and in doing so, they expand our understanding of what bosons truly are.
Let's begin with composite bosons, particles made up of other particles which collectively follow bosonic rules.
The simplest and most famous example is the helium-4 atom. It's made of 2 protons, 2 neutrons, and 2 electrons. That's 6 particles total. But here's the trick. Each of those components is a fermion, which obeys the Pauli exclusion principle. But when you add up their intrinsic spin values, a quantum property linked to how particles behave in magnetic fields, you end up with a whole number. That's the hallmark of a boson. Particles with integer spin, like 0, 1, or 2, are bosons. Those with half-integer spin, like 1/2 or 3/2, are fermions. And because the total spin of helium-4 is 0, it acts like a boson, even though it's made entirely of fermions. This is what allows helium-4 to undergo Bose-Einstein condensation and become a superfluid at low temperatures. It's not that helium atoms forget they're made of fermions, they simply move as a collective whole following the rules of bosons. But it gets weirder. In the quantum world, particles can emerge from interactions, not just from fundamental building blocks. These emergent phenomena are called quasi-particles, and some of them behave like bosons in the most bizarre, beautiful ways. Take the phonon, for example. A phonon isn't a real particle. You can't find it in the standard model. Instead, it's a vibration, a ripple moving through a solid like a quantum wave of sound. But in quantum mechanics, even a vibration can be treated as if it were a particle. Phonons carry energy, they have momentum, and they obey Bose-Einstein statistics. They're bosons born of motion. Then there's the magnon, a quasi-particle that represents a disturbance in the alignment of spins in a magnetic material. When the tiny magnetic fields of electrons in a material fall out of sync and then realign, the disturbance moves like a wave. That wave can be modeled as a particle, again, a boson. But some quasi-particles push our understanding even further. In certain quantum Hall systems, where electrons are confined to 2 dimensions and exposed to extreme magnetic fields, strange composite entities form anyons. These aren't quite bosons or fermions. They exist in a new quantum category. But when you pair 2 or more anyons together under specific conditions, they can mimic bosonic behavior. Even Cooper pairs, which enable superconductivity, are technically quasi-particles. They're bound pairs of electrons, 2 fermions whose spins cancel each other out, forming a composite boson that glides through a conductor without resistance. All of this reveals a profound truth. Bosonic behavior is not reserved for fundamental particles. It's a set of quantum rules, rules that can be followed by things we build, things that emerge, and things that arise only under the right conditions. The implications are massive. In the growing field of condensed matter physics, quasibosons are helping scientists simulate complex systems, test quantum gravity models, and build the early architectures of quantum computers. They're being used to probe the edges of material science, where temperature, pressure, and electromagnetic fields conspire to create new states of matter. In cold atom labs, physicists now create synthetic materials where quasi-particles act out behaviors we expect only in distant stars or black holes, revealing insights into the early universe or the fate of collapsing matter. Even in biological systems, emergent behaviors are sometimes modeled using bosonic analogues. Certain energy transfers in DNA and photosynthesis, for example, can exhibit quantum coherence, another boson-like trait. But beyond the science, there's a deeper philosophical ripple here. If something made of fermions can become a boson, if something that isn't a particle at all, like a vibration or a wave, can behave like one, then what does it truly mean to be a boson? Is bosonness a label, a property, or a behavior that emerges when the universe allows it? We tend to think of particles as solid, enduring entities. But in quantum mechanics, identity is flexible. A particle is defined not just by its ingredients, but by how it interacts, how it transforms, how it resonates with the fields and forces around it. Bosons, especially the emergent kind, remind us that reality is layered. What looks fundamental may not be. What seems simple may emerge from unimaginable complexity. And perhaps most stunning of all, these exotic quasi-bosons aren't rare. They exist all around us, in the solids we stand on, the wires in our devices, the superconducting loops that power our hospitals and science labs. We've engineered them, we've manipulated them, but we're still unraveling what they actually are. So the next time you think of a boson, don't stop at the photon or the gluon. Think of helium swirling in superfluid spirals. Think of vibrations in crystal lattices. Think of emergent realities hiding in plain sight. The bosonic world isn't just above us in the stars, it's within us, below us, and all around us. In the shadows of deep space, bosons govern the forces that shape galaxies. But here on Earth, inside the cold, silent chambers of quantum laboratories, these same particles are being recruited to do something altogether new. Process information in a way no silicon chip ever could. Welcome to the frontier of quantum computing, where bosons aren't just force carriers, but computational allies in the quest for a new kind of intelligence. To understand the role bosons play in quantum computing, we first need to step back from the world of classical bits, those familiar ones and zeros, and into the strange logic of qubits. A qubit isn't just on or off. It can be both at once, a quantum superposition, and it can be entangled with other qubits, meaning the state of one can instantly influence the other, no matter how far apart they are. While some quantum computers use trapped ions or superconducting circuits as qubits, others are exploring the use of photons, those massless bosons of light, as the fundamental carriers of quantum information. This is where bosonic modes come into play. In optical quantum computing, a single photon's quantum state, defined by its polarization, frequency, or spatial mode, can be manipulated to represent and process information. Photons don't interact easily with their environment, making them incredibly stable. They can travel long distances without losing their quantum coherence, making them perfect for quantum communication. But this same aloofness makes them challenging to work with. You need precision tools to manipulate and entangle them. Yet, if done correctly, photons offer a clean, elegant medium for quantum logic gates, those basic building blocks of computation. In a different approach, continuous variable quantum computing, information is encoded in the quadrature amplitudes of the electromagnetic field, a fundamentally bosonic system. Instead of discrete states like 0 or 1, these systems use continuous values. Think of it as the difference between counting marbles and measuring waves. This approach naturally fits the mathematical behavior of bosonic fields and is being championed by companies like Xanadu Quantum Technologies in Toronto. Here's where things get even more interesting. Bosonic codes, special error correction schemes designed to protect quantum information, are emerging as one of the most promising paths forward. Quantum systems are fragile. A stray vibration, a rogue particle, even a tiny temperature shift can collapse a quantum state. To protect against this, researchers are developing codes that encode information not in just one photon, but in carefully constructed combinations of bosonic states. One such scheme is the Gottesman-Kitaev-Preskill (GKP) code, which encodes a qubit into the infinite-dimensional Hilbert space of a harmonic oscillator, a system governed by bosonic physics. These codes are incredibly powerful because they allow for fault-tolerant quantum computing, the holy grail. And then there are cat states named after Schrödinger's famous feline thought experiment. These are superpositions of coherent states, quantum versions of classical electromagnetic waves, that can be used to represent logical qubits. By exploiting the bosonic nature of these states, researchers can create qubits that are more resistant to certain types of errors, such as photon loss. In essence, bosonic systems offer something that traditional qubit platforms struggle with: scalability and error resilience. By tapping into the infinite degrees of freedom of bosons, scientists can encode more information in fewer physical systems, all while building in protection against the chaos of the environment. But bosons aren't just a practical tool. They also offer new logic paradigms. In boson sampling, a type of quantum computation first proposed in 2011, photons are sent through a complex optical network. The way they interfere, thanks to their bosonic nature, produces an output pattern that's extremely hard for classical computers to simulate. While not a universal quantum computer, boson sampling has demonstrated quantum supremacy in specific tasks, offering a glimpse of how bosons can outperform silicon. There are even theoretical proposals for topological bosonic systems, which could enable fault-tolerant computing by encoding information in global properties of a system rather than in delicate local states. These ideas borrow heavily from condensed matter physics, where bosons, especially emergent quasi-bosons, behave in collective ways that can be harnessed for information processing. What's driving all of this is a realization that bosons offer a kind of quantum flexibility. They're not constrained by the exclusion principle like fermions. They can share states, they can build coherence, they can entangle in ways that make them ideal for transmitting, storing, and manipulating information. And as we push deeper into the quantum age, the importance of this cannot be overstated. Think of the implications. Global communication networks powered by entangled photons, secure from eavesdropping due to the laws of quantum mechanics. Quantum processors built from light, operating at room temperature, data stored in waveforms and squeeze states, immune to traditional forms of degradation. We are still in the early days. Many of these systems are experimental. The hardware is delicate, the results sometimes noisy. But progress is accelerating, and at the heart of it all, guiding photons through waveguides and circuits, balancing cat states and error-correcting codes, are bosons, once mere force carriers, now becoming architects of thought. There's a poetic symmetry to it. The same particles that bind the universe together may soon bind together the strands of our most advanced machines. The silent, invisible agents of interaction are stepping into the spotlight, not just as relics of cosmic structure, but as builders of tomorrow's technology. Bosons remind us that information itself is physical, and perhaps, just perhaps, the universe has always been calculating. In the intricate language of quantum mechanics, symmetry isn't just a matter of aesthetics, it's the guiding principle behind the laws of nature. Everything from the conservation of energy to the very existence of fundamental forces is rooted in symmetry. And when it comes to bosons, symmetry is not just relevant, it's defining. To understand how bosons operate within the universe, we must first confront the concept of spin. Not the classical idea of a top twirling on a table, but quantum spin, a property of particles that has no true analog in the macroscopic world. In quantum mechanics, spin is a fundamental intrinsic form of angular momentum. It is quantized, meaning it comes in discrete values, and it plays a key role in how particles interact and organize. Particles are divided into two broad categories based on spin: fermions, which have half-integer spins, like 1/2, 3/2, and bosons, which have integer spins, 0, 1, 2, etc. This difference might sound technical, even arbitrary, but it's not. It governs everything from the structure of atoms to the expansion of the universe. Fermions obey the Pauli exclusion principle. No two fermions can occupy the same quantum state. This is why electrons form shells in atoms, giving rise to the periodic table and the chemical behavior of matter. Bosons, however, obey a very different rule. Bose-Einstein statistics. Multiple bosons can occupy the same quantum state. This ability to stack, to cohere, to amplify each other is what makes bosons so extraordinary and essential. At the heart of this behavior lies symmetry. Quantum states of multiple identical bosons are symmetric under exchange. That is, if you swap two bosons in a system, the overall wave function remains the same. This is not just a mathematical trick, it's a deep statement about their nature. Fermionic wave functions, by contrast, are anti-symmetric. Swap two fermions and the wave function changes sign. This seemingly minor distinction underpins the entire structure of matter and force. Now consider the bosons in the Standard Model. The photon, carrier of the electromagnetic force, has spin 1. The W and Z bosons, which mediate the weak nuclear force, also have spin 1. The gluon, responsible for the strong nuclear force, likewise has spin 1. And then there's the graviton, the hypothetical quantum of gravity. It would have spin 2. The Higgs boson, alone among its peers, has spin 0. These spin values are not arbitrary. They reflect the type of force each boson mediates and how it transforms under symmetry operations. The graviton's spin 2 nature allows it to interact with the stress-energy tensor, the source of gravity in general relativity. The photon's spin 1 nature ties directly into the gauge symmetry of electromagnetism, specifically U1 symmetry. Gauge symmetries are among the most elegant and powerful ideas in physics. They describe transformations that leave the underlying physics unchanged, and they dictate the form of the fundamental interactions. In a gauge theory, the force-carrying bosons arise naturally as a consequence of requiring the equations to remain symmetrical under local transformations. For example, the requirement of U1 gauge symmetry gives rise to the electromagnetic field, and its boson, the photon. SU2 symmetry gives rise to the weak force and the W and Z bosons. SU3 symmetry yields the gluons of the strong force. These symmetries aren't just mathematical structures, they're why these forces exist. This is where bosons are fundamentally distinct from fermions in their cosmological role. Fermions are the bricks, quarks and leptons that make up matter. Bosons are the glue, the dynamic expression of the symmetries that govern interactions. Their ability to inhabit the same state allows them to form coherent, collective behaviors that define fields, forces, and emergent phenomena like superconductivity and Bose-Einstein condensates. And these symmetric properties have real-world consequences. The Bose-Einstein condensate, for example, is only possible because bosons can pile into the same lowest energy state. When a gas of bosons is cooled to near absolute zero, they condense, not into a physical droplet, but into a single macroscopic quantum state. The entire ensemble behaves as one quantum entity, exhibiting properties like superfluidity and zero viscosity. That's not magic, it's symmetry. Symmetry also plays a central role in modern particle physics through the concept of spontaneous symmetry breaking. The Higgs field, for instance, pervades the universe and interacts with other particles, giving them mass. But the Higgs field didn't always have a non-zero value. In the early universe, the symmetry of the electroweak force was unbroken. As the universe cooled, the Higgs field took on a non-zero vacuum expectation value, breaking that symmetry and leading to the separation of the electromagnetic and weak forces. The Higgs boson is the quantized ripple in that field, a boson born from broken symmetry. Bosons are also intimately tied to conservation laws. Noether's theorem, one of the most beautiful results in physics, tells us that every continuous symmetry corresponds to a conserved quantity. The symmetry of space gives rise to conservation of momentum. The symmetry of time gives rise to conservation of energy. Gauge symmetries give rise to conservation of electric charge, color charge, and more. And bosons are the mediators that enforce these conserved quantities. In a very real sense, they are the guardians of symmetry itself. But symmetry in physics is not always obvious. There are hidden symmetries, broken symmetries, and approximate symmetries. The pursuit of a grand unified theory or a theory of everything is at its core a search for a deeper symmetry, one that unites all the forces and particles in a single elegant framework. And bosons, with their distinct spin and behavior, are the threads from which this ultimate symmetry might be woven. It's worth reflecting on the poetic irony. Bosons, which do not obey the exclusion principle and are allowed to overlap, might be the key to unifying our understanding of everything. While fermions compete for space and identity, bosons cooperate. They echo the universe's potential for coherence, harmony, and unity. Spin, symmetry, and statistics, these three S's define bosons at their core. They aren't particles in the conventional sense. They're whispers in a field, echoes of symmetry and carriers of force. Their spin tells us how they move, how they transform, how they interact. Their symmetry tells us what they can build, how they can organize, how they bind matter into structure and structure into cosmos. The more we uncover about bosons, the more they seem less like mere inhabitants of the quantum world and more like its architects. In the dance of creation, where particles flicker into and out of existence, bosons are the choreographers, ensuring that every step obeys the symmetry of the score. And in that symmetry we find not just elegance but truth. Somewhere between mathematics and mystery lies the particle that doesn't just bind forces, but tempts us to ask why there are forces at all. Bosons began as solutions to equations, abstract ripples in invisible fields. But the deeper we've followed them, the more they seem to whisper about something far more profound. This is where science meets its philosophical edge. This is where bosons, those humble mediators of force, lead us to the question at the heart of existence itself. What is reality? Let's start at the threshold. At the Planck scale, the unimaginably small realm where space-time becomes foamy, granular, and unpredictable, quantum fields dominate. Every particle is a vibration in one of these fields. Electrons emerge from the electron field, quarks from the quark field. And bosons, they are not only vibrations of their own fields, they're the messengers between all others. They carry force, they carry influence, and they carry information. But information in a quantum universe is a strange thing. It's not just about what a particle is doing. It's about the relationships between particles, the probabilities of outcomes, the entanglements that link distant points across space. The photon that bounces off your retina isn't just bringing you light, it's bringing you a piece of the cosmos. Your very perception, your consciousness, relies on bosons. Photons relay everything you see. Gluons bind the quarks in the protons and neutrons that build your body. W and Z bosons govern radioactive decay, playing a role in the biochemistry of life. And the Higgs? It's not an agent of perception, but it's why particles have mass at all. Without it, there would be no atoms, no stars, no biology, no brain. So here we are, conscious observers composed of quantum matter, perceiving a universe through quantum interactions, mediated entirely by bosons. Is it such a stretch to wonder whether these particles or the fields they arise from are not just the scaffolding of reality, but somehow entwined with awareness itself? Some physicists and philosophers entertain a daring hypothesis that consciousness might not be an emergent property of matter alone, that perhaps in some fundamental way, the informational structure of the universe is inseparable from the experience of it. This idea goes by many names: panpsychism, quantum consciousness, integrated information theory. But all orbit a central question. Could consciousness be a basic feature of the universe like space, time, and mass? Let's be clear. There is no definitive scientific proof for such claims. But there are patterns, coincidences, and provocations that raise eyebrows. Take quantum entanglement. When two particles become entangled, their states are linked, no matter how far apart they are. Change one, and the other responds instantly. This isn't science fiction. It's been demonstrated repeatedly. It doesn't transmit usable information faster than light, but it does suggest that the fabric of the universe is non-local, that what happens in one place can influence what happens elsewhere without anything physically traveling between. Entanglement is mediated by bosons, photons in many cases, and appears to violate our classical notion of separateness. Could this interconnectedness hint at a deeper kind of unity? Could the quantum fields themselves form an invisible lattice that underpins not just matter but meaning? Then there's the observer effect. In quantum experiments, the mere act of measurement appears to collapse a particle's wave function, forcing it into a definite state. Until observed, particles behave like probabilities. Upon observation, they act like particles. But what counts as an observer? Is it a conscious mind, a measuring device, an interaction with another particle? The debate rages on. Some interpretations, like the Copenhagen interpretation, leave this ambiguous. Others, like Wigner's friend thought experiment, push the boundaries further. What happens when two observers observe the same quantum event differently? Are there multiple realities? Does consciousness collapse the wave function or merely reveal it? Again, bosons are central. They're the agents of interaction. The collapse of a quantum state is, in effect, a transfer of information via a boson. When a photon hits a detector, or an eye, or a piece of film, it's not just energy being transmitted, it's a resolution of uncertainty, a commitment to one outcome among many. From this perspective, bosons begin to look like more than just passive carriers. They are the active stitches of reality, choosing, collapsing, updating the state of the universe with every interaction. They are the reasons things happen the way they do. This doesn't mean bosons are conscious, but it raises a tantalizing possibility. That reality, as we experience it, is a byproduct of quantum information exchange. That existence, moment to moment, is constructed not out of stuff, but out of relationships, out of measurement, out of meaning. And this has staggering implications. It suggests that what we call the physical world is not an objective stage on which events unfold, but a constantly evolving tapestry woven by fields and particles and the interactions between them. Bosons, in this view, are the needles. There's one more angle to consider: symmetry breaking. We've talked about how the Higgs field broke the electroweak symmetry in the early universe, giving mass to particles. But symmetry breaking is not just a cosmological event. It's the engine of complexity. It's why the universe isn't uniform and featureless. It's why stars form, why galaxies spin, why life can emerge. In every case, a symmetric, undifferentiated state becomes structured and specific. Possibilities collapse into patterns, and at each phase transition, from energy to matter, from matter to life, from life to thought. Bosons are there, mediating, enabling, making it possible. Perhaps the deepest question isn't, are bosons real? It's, is anything else? Because in a quantum universe, what we perceive as solid, tangible, definite, is anything but. Reality is built on probabilities, collapsed by interactions, observed through fields. The world you know is an illusion cast by wave functions and woven by bosons. And yet, it works. We build machines that run on quantum principles. We detect bosons. We use photons to carry messages across oceans. We manipulate their states to store data, measure time, and explore the universe. They are as real as anything we know, perhaps more so. In the end, bosons may not explain consciousness, but they remind us that the universe is interactive, that nothing exists in isolation, that meaning arises from connection, and that even the emptiest vacuum teems with potential, not of particles waiting to pop into existence, but of questions still waiting to be asked. So the next time you look at a star, remember this: the light that reaches your eyes crossed space as a photon, massless, eternal, unchanged. It began its journey as a boson, and in the moment it touches your retina, it becomes part of you. Information, energy, awareness, all linked by a single quantum exchange. And in that flicker, in that brief collapse of possibility into perception, something astonishing occurs. Reality happens. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.